All right, to finish off 5.2, we're going to dive into some problems for rotational inertia. I tried to make these kind of complicated, so we can be pretty efficient here. Two children of masses 25 and 30 kilograms ride a circular playground ride that has a mass of 150 kilograms and a radius of 1.3 meters. If the children ride on the edge of the disc, calculate the rotational inertia of the system. Use iota equals 1/2 mr squared for the ride. So what I want you to keep in mind for this problem is that the rotational inertia of this system is the rotational inertia of the ride plus the rotational inertia of the children. So the iota for the ride plus iota for the children. And so what we're going to do, as it says, we're going to use 1/2 mr squared for the ride, and then we're going to use m of the first child times, they both ride on the outside, so we're going to use r squared, plus the mass of the second child times r squared. Now, if the children are distributed differently, we need to use different values of r, but they're all the same in this one. So 1/2 times the mass of the ride, which is 150, times the radius of the disc, which is 1.3 meters, and we'll square that. We're going to add to that the 25 kilogram mass child times 1.3 squared, and then the 30 kilogram child times the 1.3 squared. So all are at the same value of r. And that gives us a whopping 220 kilogram meters squared. That's like a pretty large rotational inertia for something that is like human sized. The values get much larger, and in our lab, those values are going to be much smaller. All right, so for the second problem, it has two parts, and it says spheres of masses m and 2m are attached to a bar of mass 3m and length 2l. Use this expression for the bar. Derive the rotational inertia of the system when rotated about its center. So I'm going to draw what that might look like. We have m over here, we have 2m over there, and a length of 2l, and our axis is going to be through the exact center. So again, similarly complicated, we're going to calculate this rotational inertia. I have to do the bar and then add in the two spheres. So I'm just going to jump right to some formulas. 1/12 ml squared for the bar. So 1/12 times a mass of 3m, that's the mass of the bar, times the length of 2l, and that's going to get squared. And then I want to do each sphere. Each sphere is actually a distance l from the axis, so this is just going to be ml squared, and the other mass is going to be 2m l squared. And I just need to add all of that up. So 1/12 times 3 times 2 squared is actually 1. So the rotational inertia of the bar is ml squared. 2 squared is 4, times 3 is 12, times 1/12 is 1. Plus ml squared plus 2ml squared. And so the rotational inertia of this whole system is 4ml squared. So that's when rotated about its center. The second question now says derive the rotational inertia of this system when rotated around the end with mass m. And the way that I've presented it, you have to use the parallel axis theorem. If this bar were massless, you could just use the definition of rotational inertia. So anyway, I will skip to that in just a moment. So now what we're going to do is we're going to take the same object, and or rather same system, and we're going to now rotate it around that left edge. The old axis was here, and so the distance, the axis got moved, is from the center to the edge. We did the same thing for the other problem, but it ends up turning out a little bit different. So we'll use the parallel axis theorem for this one. Again, because we already know the rotational inertia around the center of mass, we're going to now rotate it not rotate, we're going to now move the axis to a different location. So the parallel axis theorem is going to be most helpful. I want to be a little careful here. The new rotational inertia that I'm going to find using the parallel axis theorem, I have to use it for just the bar, because I'm using the rotational inertia of the bar to do this. These masses I need to consider after the fact. So I'm just going to do this in 2 steps. So this is going to be the rotational inertia of just the bar rotated around its center. I already did that work here. So I'm just going to take the result, which is ml squared. That was the rotational inertia of just the bar rotated around its center. And now I'm going to add the md squared term. The mass of the bar is 3m, and the axis of rotation was moved this distance d. Now the whole bar is 2l in length, and so the axis was just moved a distance l. These are like terms, as they always will be. So ml squared plus 3ml squared, that's 4ml squared. Now that's just the bar. So maybe I'll note that, and you can note that in your notes, that just for the bar. Now I also have to update the rotational inertia of each individual sphere. So I can do that by imagining I'm going to calculate the entire rotational inertia again. So I start with the bar. That's going to be 4ml squared. And now I have to add in the inertia of each sphere. I'm going to skip the sphere of mass m because it is now located at the axis, and so it will contribute nothing to the rotational inertia. It's this mass of 2m that now contributes more rotational inertia. So the mass of that is 2m, and it is now located a distance 2l from the axis of rotation. So I'm going to now add these, 4ml squared, and then this is 2 times 2 squared, ml squared. So 2 squared is 4, times 2 is 8, and so this is essentially 4ml squared plus 8ml squared, getting me 12ml squared. So the rotational inertia went up considerably by moving that axis. It increased the inertia of the bar, and it increased the inertia drastically of the 2 spheres, from 3ml squared to 8ml squared. And that's that.